found the metal layer battery, so you just remember two terms. One is the oxygen reduction reaction, ORR in short, where typically what happens, oxygen gets reduced with the help of some catalyst to the water is mainly, but here it is written as like hydroxide ion. So oxygen gets reduced, and in as a counter reaction, you know, once it is redox reaction is happening, then one is oxidation and another is the reduction. So if oxygen is getting reduced, then the other side metal, basically here like zinc, is getting the reduction oxidation. So this is a combined oxidation reduction process, but driven by the oxygen partner. And at the same time, in the anode, which is oxygen evolution reaction, in short it is OER, where the water molecule basically get oxidized and results oxygen evolution, which ultimately release the 4 electron. Now the important point is that when the reduction reactions happens, oxygen reduction, as you know or you might have experienced, that once you do the reduction reaction, it release the energy, right? So in the battery point of view, just I am correlating, in the battery point of view, once the reduction reaction happening, it release the energy, or you can say you can utilize that energy. And when oxygen evolution reaction happens, it basically works for the charging the battery. Okay, so uh, in the primary batteries, so what your batteries you are using, I'm using here pencil cell even in this, what your battery you are using in your day-to-day life, which you cannot recharge it further, that categorize under the primary batteries. And the other one, which you can basically further recharge it and reuse it and keep doing the same thing, that comes under the secondary battery category. Again, in the primary battery, the main function happens at the reduction, not oxygen, but some sort of reduction. So if you just take example of, let's say, pencil cell, then there you find like zinc will be oxidizing to the zinc oxide, and manganese oxide getting reduced at the other end, and you get the energy. And that is not since rechargeable, so you need to use it. Once you find the electrolyte ammonium chloride, mainly when it becomes black, you need to just throw it out, right? But if you see the other part where the it can be recharged, then along with the reduction reaction, oxidation reaction is equally important and efficient. So once the battery get discharged as the results of reduction reaction, then at the second end it start oxidation reaction, again oxygen evolution reaction in terms of metal layer battery, then it gets recharged. So you can keep on using those batteries. Okay, so this is just a basic principle for the rechargeable metal layer batteries. And since oxygen is abundant, so this has really a potential to change the energy landscape if it can be properly addressed and utilized. Because having such catalyst which can work in terms of stability, in terms of efficiency, in terms of non-hazardous nature, if can perform both the function or individually, then it can really solve a big problem related to the renewable energy. So there are a couple of reports where people are claiming to use such batteries for different purposes, especially in vehicle. So you can find it all around in the internet. But the important point is that particularly why the zinc air battery becomes much more important, because of course zinc is abundant, especially if you see geographical region, then India is the 4th largest producer of the zinc, okay, worldwide, and it is safe, it is much cheaper. So this really attracts a lot. Now I will just uh, focus a little bit on the basic design of the molecule in order to get the property which can perform oxidation reduction reaction as well as evolution reaction. So if you consider a conjugated microporous polymer, which basically name itself suggests, first term is the conjugate redox active. So redox active means you have to have two units where one is act as electron donor, the other one can act as the electron acceptor, right? Then only you can get the redox active properties. The second thing is the conjugated. You all are chemists, so even physicists, so you can know better that it has a continuous conjugation, and then only it can help to flow the electron from one end to other end. Then the microporous. Now here you can consider this like a pore, okay? So which basically helps again to provide the high surface area, to facilitate the substrate diffusion inside the pores. So eventually you will be ending up a better efficiency as compared to the non-porous material. And the last but not least, one of the important parameter is the substitution at the organic linker. So since it is like a complete organic framework, so you must take solubility, stability in the account in order to design the framework. So for example, there are some framework or molecules which are excellent in property, but you cannot dissolve them or you cannot make the blend properly. So for example, like lot of fluorinated products. So you need to tune in such a way. So sorry. Okay, you need to tune the substitution in the organic linker in such a way so it can balance a very nice way to get the very good film or layer or whatever you are going to make. Now if you have taken these things into account, it can form like 2D layer kind of a structure, and since you have substitution, you have porosity, so ultimately you can expect a nice outcome. This I'll not talk because already Professor Zaz has told several times about semiconductor nature. So where basically you generate a whole pair where valence bond and conduction band. So basically the electron will be going from valence bond to conduction band, and that has to further flow rather than coming back in order to get the electricity. So this is again, considering the design principle, now I'll be just going through a proper investigation where how you can have a property of ORR and OER catalysis in a molecule or in a material which can perform both the reaction or both the activity. So as I mentioned, it should be redox active, and one of the very nice molecule for the redox activity is triphenylamine, which is having nitrogen in the center, and that can basically roam around basis on the need. So basically you have 3 amino group, and the lone pair of the central nitrogen is free to basically switch towards those amines. And if you basically connect it with properly conjugated linkers, and now here if you see the difference, the one linker which is called as like a mix, that is having 2 alkyl chain. One side it is glycol, the other side is having the only alkyl chain. The other one having glycol chain both the sides. Now you will see just a small tuning in the side chain, how it basically results in the property. So this is the characterization things which you can leave. Only important point is that if you have a mixed side chain, that end up with kind of agglomerated or globular morphology, but the glycol chain in the one which is having both the side resulted in a very nice fiber kind of morphology. and you are continuously listening since morning that if you have a narrow wire kind of morphology, or which can basically provide you high surface area, that can enhance the property together. So just a small change is resulted the different morphology. Now once we perform the ORR reactions, we found that the mixed one and if you compare the performance of mixed one and the diglycol one, you can leave other things for time being, but you see the current density under the very similar condition. The one which is having the morphology or nanowire kind of morphology is giving better ORR reaction. So that means, again, the proof of a fundamental concept that if you have a large surface area by any means, you can get the better performance. It both has shown tested almost 12 hours, and which has shown a very good stability as well. So now we have a material which is ORR active. Just remember the core moiety of triphenylamine. Similarly, based on the literature, we found that getting ORR activity actually is much more difficult than the ORR. As compared to ORR, getting OER activity is much more difficult. Now, for the OER, based on the available literature, we found that if you take the cobalt, which is again redox active metal, this shows very good OER activity. But the only thing, you have to have either cobalt, metallic cobalt, or atomic cobalt, or even some nanoparticles. You cannot have simple salt of, let's say, cobalt hexachloride. Okay, so here we have taken phthalocyanine and we have encapsulated cobalt in the main core. The other moiety remains the similar. Morphology here we got almost layered one, but the important part is that we got OER activity from this material, which is having cobalt in the core. The OER is giving almost the current density of, let's say, 13 milliamps. Now, out of this, the most important, like Toffel slope, which is giving the information about the reaction kinetics. So it is having around 87. If you see the literature, then it is really found in very good place. So now we have two materials. One is having basically cobalt base, the other one is having the triphenylamine base, and one is showing ORR, another is saying OER. Then we have another design where we tried to put in such a way so we can have both together. So in this one, using fluoroglossinol and again triphenylamine as a precursor, we got again a redox active polymer, where you can see that fluoroglossinol is like electron acceptor and triphenylamine remains as a electron donor. Then, and as I was telling that this material itself is a ORR active, but not OER. However, if you dope the cobalt nanoparticle through whatever way you want, even if you have triphenylamine, you don't need to add any reducing agent. It works itself as a reducing agent and it forms the cobalt nanoparticles. Now, if you have cobalt nanoparticles on the other hand, it gives the activity for both. ORR driven through the triphenylamine and OER driven through the cobalt nanoparticles. And this is the data. So basically cobalt nanoparticle stabilize on the surface of triphenylamine. Okay, and you see the ORR and OER both are giving reasonably good, but I have not shown the data, but if you see the stability towards OER, then it remains moderate because these are the nanoparticles. Over a period of time or over a several cycles, it start leaching out, right? So maybe after 12 hours or 14 hours, you will find that the cobalt nanoparticles leaching out from the material and you are losing the activity for the OER. Then we thought, okay, let's have some more fun and try to coordinate the cobalt in the framework rather having the nanoparticles. So we have another OPE linker where we have chosen the pyridine derivatives. Now once we form the polymer from both of them, it gives a imine kind of bonding, and also it gives opportunity to hold the metal ion as such. And indeed this material has binding capability with the metal side. After all this characterization, which I am not going through, we found that using similar ways, this gives a cobalt coordinated framework, porous organic polymer. Now we have seen through different analyses that this is having almost 2.5% of cobalt chloride, which is bounded through these two nitrogen. So forming basically 5-membered zinc kind of things. Okay. Then once we perform the activity first with bare polymer without the metal, it was giving the OER activity, you can see just only 3 milliamps current density. But once you have cobalt in the framework, coordinated cobalt more precisely, it gives almost 100 times better, or 10 times, sorry, 10 times better OER activity. Okay. Now the current density is around 30. In previous cases, if you remember, it was maximum 12 or 13. Okay. And even TOEFL slope was much better. Stability also for this one was excellent. Okay. So we found a material which is having both the individual property of oxygen reduction as well as oxygen evolution in such a way, so it is stable now, it is having sufficient doping and nice performance of ORR and OER. Now once we elucidated the mechanism, we found that for the ORR only nitrogen of the triphenylamine is responsible. So we found that although cobalt is available, but the oxygen remains with the triphenylamine due to presence of the electron at the nitrogen center, and this is responsible for the oxygen reduction. However, for the OER, the water molecule goes to the cobalt center and it performs the OER. So it again proven that both the individual property important to perform the bifunctional activity. Using this, we have constructed the zinc air battery. I'm not the expert in battery particularly, but one of my colleague in the same lab has constructed, since we got the basic fundamental fulfilled for the battery. Then we have used zinc basically kind of sheet, okay, which works as a redox active and balance both the reaction as a counter reaction. Okay, so one sided, the same material, one sided coated, where it performs the oxygen reduction reaction, the other side it is coated and it gives the oxygen evolution reaction, and in the middle zinc layer remains as such to balance both the reactions for the both side. Now zinc air battery performances, open circuit potential was 1.35 and specific capacity was 837, which is comparable with the market available products. Important point is that if you see the charge discharge curve, that was performed almost 18 hours. So basically one side it is charging, another side it is discharging, and that represents directly ORR and OER reactions. So if you see, although at the end of 18 hours the graph remains broader and it shows that now it is taking much more time compared to earlier, but still it is with the range of charging and discharging. For illustrating the practical application, I will tell you, we have constructed with I think 3 or 4 milligram of the product. this battery with all the jugaad technology, and we found that two LED, a small LED, was able to lit for 48 hours without further charging. And of course, it get discharged after 48 hours. You leave it for a few hours, you again start, it will again lit. So point is that since oxygen is available in plenty, it it is kind of self-rechargeable or self-driven or self-breathable battery, which doesn't need any extra charging from electricity support. You just leave it for some time. It will take the oxygen from air. It will keep doing the OER, and at the end of OER, you will get your battery get charged. Now you can use the electricity, it get discharged over a period of time, you again keep it for some time, it get charged. So that's the cycle works independent to the any energy source. So that was the overall picture. So summary, we started or I started here to show you a material having redox activity connected with the triphenylamine that was only ORR active. Then we have cobalt integrated in the material which was showing only OER. And the third one where we have both the property TPA, triphenylamine and cobalt but as a nanoparticle. It was active for ORR and OER but having low performance as well as poor stability. But in the fourth design where we have triphenylamine and cobalt is integrated as a coordinated form, atomic form in the framework, that was showing excellent performance and nice stability towards the zinc air battery, and we have successfully constructed that. So with this, I will acknowledge my postdoc supervisor, Professor Majhi, for great support, and he was the person behind all this study. And of course, funding agencies, UGC, SCRB, and a big thanks to all of you. Thank you.
Thank you very much, Dr. Ashish sir. Very nice and exciting work, lot of big pictures, lots of data, and you have done tremendous job.
Thank you.
So with that, is there any question? Yeah, please. Yeah.
Thank you for interesting talk. For just a general question about zinc air battery, so you need to maintain the oxygen level in this battery because oxygen is getting like released, isn't it? Or
So this was having a kind of breathable film, which was basically taking care of releasing the oxygen after the OER,
okay,
oxygen evolution.
so you need to keep the oxygen
No,
flow in
no,
that.
no, 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 no. It's only from air without giving the extra concentration of oxygen. It was working nicely. Yeah, thank you.
Yeah.
Sir, very nice one. So one just query, how many times that can be recharged?
So you mean the final battery setup or okay,
I received that.
okay. So at least we have done twice, thrice, but I mean we should check more often and more periodically. But even after twice, thrice means after a week time, we did not get any degradation in terms of the efficiency. It is like a very basic level at this moment, but definitely if we can imagine like within the 3 milligram of the product we are able to lit 2 LEDs, then if we take let's say 100 means a milligram or even more, we can think of a better application because we have at least done a small motor in the lab using the battery, this battery. So we had that much. Thank you.
Thank you, sir, for giving the very good and insightful explanation.
Thank you, sir.
So now we will have another lecture about battery electric. Okay, so if you need to Thank you, Sarma sir, for the kind introduction. I welcome Professor Raj and guest for Dr. T.P. Binod sir and head sir. And thank you, students, for your kind presence. So today, I'm going to show from my some PhD work, which I've done in IISc. So here, the talk is going on nanotechnology. That means some materials at nanoscale. So I am going to talk on molecules, not materials. So molecules, can we make molecules of nanometer size? Normally it is smaller than the, like if you check one molecule, so that size will be in Armstrong or picometer range. So if we stitch the molecules, several molecules, so it also may form molecules of nanometer size, which is called supramolecule. So in my talk, I'll give some light on supramolecular self-assembled cage, self-assembly process I will explain. And next, I will go to some example of the supramolecule. So one example is metal barrel, like metal coordinated structures. And another next, I will go to some pure organic cages. That also you can prepare. So two example we'll show here. One is metal coordinated, another is pure organic. So, what is supramolecule? If you check the structure, this is dodecahedron it is called. And it can be formed from combination of a pentagon, two-dimensional sheet. So it can form a dodecahedron. So on 2D structure, you can prepare a 3D structure with a definite shape and geometry. So our also approach is to prepare supramolecule. We'll start from small molecular unit. Maybe the size is 0.1, 0.2 nanometer, very small angstrom scale. And if we can get a supramolecule which may have 1 to 10 nanometer diameter range, if it is macromolecule, large molecules. And can we control for that? Because we know synthesizing molecule is not a easy task. So quite it is hard to synthesize large molecules. So now in this session, we'll see some examples how we can prepare a large molecules which have nanometer size diameter. So first of all, I must say about the Nobel Prize in 1987, where host guest chemistry was recognized by Cram, Lane and Peterson. They were awarded because they have shown the importance of macromolecules, which is called supramolecules, and their molecular pocket. For example, a crown ether, everybody knows the crown ether. It has a two-dimensional structure and oxygen atoms. So based on this size of the crown ether, it can selectively detect metal ion, can bind metal ion. For example, a 4-member ring, 4 oxygen member ring bind lithium, 5-member sodium, and 6 oxygen atom bind potassium selectively. Cryptant, it is a molecule, one of type of molecule, it can bind potassium ion, ammonium ion. So what you can see the applications is that this supramolecule can detect and bind at molecular level, which is not possible for. So next, I told that how to synthesize these molecules. So one of the most common process is called self-assembly. Self-assembly means where the molecular units, they automatically reorganize to give a symmetric structure. For example, you see my cell. My cell, it is forming from a single unit where it has hydrophobic and hydrophilic unit. So it organizes so that hydrophilic head outside and hydrophilic inside, so it give a spherical structure. DNA, it a double strand structure. By hydrogen bonding, it can form. So similarly, if we give small molecules and a driving force so that it will reorganize to give a definite shape, so that is called the self-assembly process. So there are so many design principles. I will talk just 2-3 examples. So one is hydrogen bond, that DNA, it is like we have seen. So hydrogen bond, using hydrogen bond also, several macro cycles, like 2-dimensional macro cycle. It is not an extended framework, it is discrete molecules. You see, this kind of a hexagonal molecule can be prepared by hydrogen bonding interaction. Next, another important is coordination. architecture. So where you see there is two unit people are using, acceptor and donor. Donor containing organic molecule which have donating site, chelating site, and acceptor has a metal counter and a metal part, and also there we are giving the direction. That means if you take this metal as platinum or palladium, so it has a square planar structure. So if we block one or two positions and open other two positions, then it will directionally bind with the ligand. So this is the strategy. So you see how we can make the 2D and 3D ensembles. So for example, if we take this molecule, this is a palladium or platinum if you think, this is called 0 degree acceptor, like this molecule. Here it is P83, and if you take a nitrate, so nitrate easily can remove. So it will act as a 0 degree linker. So with this, and this is the, if a linear ligand like this, it will give a square like this. So like this way, it can give a several two-dimensional and three-dimensional architectures. Some of examples if you see, people have done this kind of ethane diamine nitrate acceptor, and some this kind of tetrapyridyl ligand. So this molecule, when treated with palladium ethylene diamine palladium nitrate, it is giving a barrel-like of structure. Barrel means all four faces are composed by this ligand molecule, and vertices contains the metal atoms. And it forms in 100% yield sometimes. So we'll go the example, for this example. You see, this is a porphyrin molecule, and 4 pyridine unit is there. When it is bind with ferrocene-based platinum acceptor, it is 90 degree acceptor. See, angle between this is 90 degree. This is two leaving group, counter anion. So when it is binding, you see, in vertex it can sit, and it can give, and because it is ferrocene, it can expand its bond angle, and it is giving a hexagonal structure. That means a hexagonal barrel. All the 6 phases are composed by this ligand, and vertices by the metal. So what is the utility? Why you are doing that? Utility of the means metal coordinated architectures. So because of this, if you see, this molecule contains hydrophobic unit, organic molecule, as well as metal counterparts. So metal counterparts also have high charge. If you see, this platinum is +2 oxidation state. So when this structure is forming, it has, so 12 into +2 means +24 charges. So this make it is water soluble. Instead, it becomes water insoluble, because you know organic molecules are water insoluble. So after forming the cage, this molecule becomes soluble. So I'll show some examples. Let's see this molecule. This is TPE, tetraphenyl ethylene, 4 phenyl group. Tetraphenyl ethylene with 4 imidazole, which can bind by this nitrogen atom. Now this molecule, if you react with tetramethyl ethylene based palladium acceptor, it is a 90 degree acceptor, so it can give a trifacial barrel in 100% yield. So you have to just mix the two counterpart in 50 degrees centigrade in water, just stir in 50 degrees centigrade, keep it for 12 hours or 8 hours. You will get a water soluble compound which is 100% this barrel compound. I will show some characterization technique, so you can check that this is actually forming. And because of forming this structure, you see, in water it is soluble, and it has hydrophobic unit, so it can provide a hydrophobic pocket. So you can see a space, no? Inside this, there is a 2 window above and below. So in this, in water, you know, if you now give some guest molecule like this catalysis has done. This is naphthaldehyde with this diamidine molecule. So now see, these two molecules in water will not react, because in water it is insoluble. But in presence of this architecture, this two is going inside to the barrel. So it is like container, vessel, the molecular vessel. And inside this, when it is going, there is proximity. So very quickly, very fast the reaction is going. And once the reaction is going, it is going to bigger size, and it is coming out. So this barrel is acting like a catalyst. by simply giving the reaction space where two substrate can go and react between them. So I will, and next, as I told that I will show some organic example also where this expensive metal pickers are not used. So there are some organic molecules people try to synthesize. Physically it is possible, not like cube and dodecahedron. This has been synthesized, but here the difficulty again was this is CC bond, and it is very difficult to synthesize in 100% scale. So this dynamic covalent chemistry, this concept then solve this problem. So this concept is that if you mix two precursor, it will give product to 100% yield. Why? Because if any other product it is forming, it is dynamic bonds. So it will break and go back to the substrate. Then again it will give to the your desired product. So one of the examples is imine condensation reactions. So imine bond are very reversible. So if it gives something else, it can go back and again it can form your desired structure, symmetrical structure. So okay, so this is some examples people have reported. Okay. So this structure, for example, you can see it is a nano ball kind of structure. This is a crystal structure. So, and the size is around 3 to 4 nanometer of this molecular ball, and they have used this as a active surface molecule, where here they have done photooxidation catalysis using these molecules. Like if it contains some photoactive group, like here. So by using this functional groups property, they can use in several applications. So next I'll go one of my work which I've done. So based on this, what I've explained, that coordination architecture structure, I have synthesized this barrel. I could able to synthesize this barrel. Barrel means tetrahedral box actually, where two side is open, two end side. So the idea was again same. It should have a open window so that guest can easily go inside, and after reaction it can go outside. So this was some reaction scheme. So this tetrapyridyl ligand was synthesized by this condensation reaction. So basically this is a thiamide core, and it contains 4 tetrapyridyl units, so which can bind with palladium, and upon reacting with both palladium and platinum acceptor, in both case it is giving a barrel, but unfortunately in one case, for palladium case, we get water insoluble barrels, and for platinum, well, it has more high potential charge, so we got water soluble barrel. And with this, because it is water soluble, we have checked some applications, some host guest chemistry, because I have seen that in earlier case we have seen some guest in aqueous medium can go inside to the barrel. So for that, what guest we have choose? A photochromic guest, like DASA. Photochromic materials, you know, it is very useful. Okay, because in presence of light, it can switch the structure, and by using that property, we can do several materials. So this DASA molecule, this is called donor acceptor Stenhouse adduct. It's basically a amine counterpart in and dicarbonyl counterpart. So this molecule, it give color change and also structural change by just irradiating visible light, even not UV light. So this is DASA molecule, and by changing solvent. So this one type of photochromic molecule which change their structure, okay, in presence of light or solvent. For example, this linear structure, this is stable in organic solvent because it is organic. And when it is going to another structure, converting, it is dipolar structure, plus minus. So it is not stable in organic. So in organic solvent, you will see red color because it is conjugated. In protic solvent, aqua solvent, you will see a yellow color. So by solvent changing, you can see 2 colors. And also, in organic solvent also, this red solution, if you keep under visible light, slowly you will see yellow color is appearing. Because by light irradiation, this forms a deuterionic structure, which is not stable, but it forms by presence of visible light. So this is reversible process in organic solvent. So our idea was, in water, this is not reversible. Why? because this is deuterionic, so it will be very much stable in water, and it will not like to go back the neutral form. This is linear form. So in water, this reversible process become irreversible. So our idea was, can we make this irreversible process in water is reversible by using our barrel. So what we have done, so this is characterization technique. I will not go to that because we don't have time. So okay, better going before that, I will show the crystal structure. So first I have characterized by NMR and mass, and not only that, this single crystal XRD structure of TB1. We practically have seen that this kind of barrel it is forming, and if you see the dimension, it is like 1 point diagonal. The diagonal diameter is 1.9 to 2 nanometer. You say 2 nanometer diameter it has this barrel. So this barrel has enough molecular pocket to host a molecule. So for that, we have utilized this in this kind of isomerism property. So what I have explained that in this guest, what I have shown, that guest in water it is yellow color because of deuterionic form. So now if you keep in dark, or if you irradiate light, anything if you do, it will not, color will not change, because this is stable deuterionic structure. This is deuterionic structure. What I've done, when we are adding our barrel to this water soluble, so just after adding, it is getting soluble, and after getting soluble, it is giving the red color. So that means the deuterionic form slowly converts to the open form, linear form. And reverse also we have done. We have taken solution of barrel in water, to that in solid state is open, red color, then red solid when we have added, it should go in water, it should go to the yellow color, polar form, but it is being stable inside the barrel, and it is staying in the linear form and giving the red color you can see. So this is the applications, and we have characterized the host guest ratio, other things. Okay, we have done 2D NMR. We have optimized their host guest structure also by doing DFT analysis. So how the guest can align inside the pocket. And this is the conclusion of this work. And here we have seen that metal coordinator architecture can do some host guest chemistry in water. That is very useful. But the problem is that the metal bond, this is not that much stable. It decomposes in presence of acid base. And also it involves some costly platinum palladium, which have square planar architecture, square planar geometry. So those are very expensive. So I also tried to prepare some purely organic structure, which is very not expensive. It's very cheap materials, aldehyde, amines, those kind of molecules, if we can prepare a large molecular architecture. So for that, first I will show this molecule. This is called some hexaldehyde, like this is isophthaldehyde, and 3 units we have merged here. And here I have tried that imine condensation strategy. So on aldehyde I am forming a prepared, it is building unit, and I have mixed this with this diamine. This is called cyclohexane diamine. So, and we expected a symmetrical structure. So we will see what it is forming actually. And we have seen actually this kind of architectures, tetrahedral cage. It's a big nano cage, around 2 nanometer diameter it is having. And you see all the hexaldehyde, it is situating at the face of the tetrahedron. Like 4 face, a tetrahedron has 4 face, so 4 face it is sitting, and in vertices, so 3 diamine unit is sitting, and giving a tetrahedral structure which have a void inside it. So this characterization technique, I'll not go. I'll also show some DFT analysis. See this, if you imagine a sphere inside the tetrahedral cage, the diameter is getting 1.34 nanometer, which is not very small, like molecular level. It is giving 1.34 nanometer diameter size. So, and okay, next slide it is there. Oh no. Chirality also. So this is something different. Is that this hexaldehyde? It was achiral. After forming cage, it is giving chiral cage. So it is chiral induction, and then chiral induction is happening from the cyclohexane diamine unit. So that cyclohexane diamine we have taken the enantiomer pure, and that enantiomer pure cyclohexane diamine, this one, this is a achiral aldehyde. But after forming cage, this chirality, it has transferred from cyclohexane diamine to cage, and that's why we are getting two enantiomer pure cage. Like if you are taking RR cage, we are getting one isomer. If you are taking SS diamine, we are getting another isomer. So in stereochemistry point of view, we can synthesize a enantiomer pure cage without using a enantiomer pure substrate, means aldehyde unit. Anyway, so again, I'll go back to the our main topic, nano material. So here, because it has a pocket, and also it has cyclohexane diamine, means all nitrogen atoms which can complex with metal atoms. So we tried whether we can prepare some complex or nanoparticle, whether this cage can interact with some metal precursor. So what we have done, this cage we have taken in chloroform soluble, and we have added palladium acetate. So here oxygen stage +2 palladium acetate salt. What we have seen, it is giving yellow color, so which signals that some complexation it is forming really. So this, because this cyclohexane diamine unit, it can complex with palladium, so we can see some complexation. And when we are next adding sodium borohydride, it is giving black color, so which indicates that this +2 oxidation state is going to 0 oxidation state, and it is giving black color. Now the question was whether it is nanoparticle, nanomaterial or not. So we exclusively characterize these materials whether it is nanomaterial or not. So it oxidation state, particle size, morphology, all we have checked by TEM, SEM and EDX express spectroscopy. So this is the TEM, you can see it is forming a homogeneous size of nanoparticle, this black spot, which is having this distribution 3.5 plus minus 0.3 nanometer. So we are getting a nanoparticle with controlled size. So this is very tiny size, and which we can control by using a cage structure. Just simply giving the metal salt, and after reduction it is giving your nanoparticle in very smaller size. And oxidation state also we have checked that it is 0 oxidation state from the 3D/2 and 3D5/2 value. And this is the morphology. You can see that this is a amorphous material. And next, this nano catalyst, this nanoparticle we have used as catalyst, because nanoparticle has application in catalysis, so we have checked. Because nanoparticle can do catalysis, so we have checked some catalysis, and this catalysis we got around quantitative yield in DMF water medium under 100 degrees centigrade heating conditions. And we got a quantitative yield, and substrate scope, if you see that all cases we are getting more than around 90% yield for all cases. And not only that, this nanoparticle was stable for recycling also. We have checked three recycling. You can check the yield is changing for first cycle, conversion 99 for 98, 96 like that. So conversion was going to quantitative almost after 3 cycle also. You have checked the material after recycling also, the material TEM image, which show that it is having around 3.6 nanometers. So size is not that much changing, leaching is not happening, and the nanoparticle becomes stable in presence of cage template. So in this case, so we have done the synthesis of cage in quantitative yield from very cheap material, and which able to catalyze this homocoupling reaction, and recyclability also shows a good amount of yield. So in acknowledgement section, I will acknowledge my institute where I have done PhD and masters, and my supervisor, PhD supervisor, Professor P.S. Mukherjee. Now he's associate editor of Inorganic Chemistry Journal. Like that, I'll thank the audience. Thank you. Right, sir. Right, sir. Good point. In all cases, we are checking the stability after reactions also, or after catalysis also. We have checked that cage is not breaking and it's stable. Unless the, yeah. So that again it is coming from the designing principle. I will go to quickly to the designing principle, sir. For example, okay, this okay, okay. For example, this one. So this acceptor is designed in such a way that it can accommodate 90-degree angle. Square planar metal. So one C side is blocked, another C side is open. So 90-degree angle. And this is a stable molecule which is planar. So in plane it can coordinate. Now it if can hold 90-degree angle and these two can bind, then there is no strain. Because it can hold, because it is like this 90-degree angle and the faces like this it is binding. So that way the design principle coordinator architectures it has designed that some all are not alloyed, all geometry. So it depends on the donor acceptor binding angle. So based on the angle it will give the structure which is more stable thermodynamically, because there are several possibilities when both are mixed. So this is that's what is called self-assembly. So it is self-assembled to give a unique one structure. We are not controlling the structure. We are giving the geometry in the direction. So in that direction it is forming. Right. Right, sir. Actually, what we thought that nanoparticle will form inside the cage pocket. So actually, we did not see that. So that part, it is good like observation point, sir. So nanoparticle size, if you see, it is 3.5 nanometer. 3.5 nanometer, and diameter what we have calculated by DFT, it is 1.34, like if you spare, if you consider. So it is actually multi-component, multi-cage are supporting the nanoparticle. So it is vertices, because vertices has the complexation unit. Yeah, for this case, there are also some examples. Single cage inside pocket it can accommodate, because size if you can check, it is smaller size, in annual size is smaller than the pocket. In this case, because the vertices it is containing the complexation unit, binding unit, so that's why at corner it is forming. And when it is pair it is forming, so other cage also can support from outside. Yeah, like some case we check dozy complexation. Like dozy means a two-dimensional NOS spectra, so we can check, can differentiate the molecules based on the diffusion. So when we check the palladium acetate this complex, cage complex, it is showing a single line, means single diffusion coefficient. That means entity is 1. If it is different, it will show two different coefficient. Like this is the spectra. Like this is called dozy NMR. For cage I have shown here. Like all the cage peaks, these all are cage peaks. These are having in same line, and this is solvent peaks. It is staying in another line. So for dozy also can show on. Also IR spectra also we have done, and mostly theoretical. Like we are getting experimentally 3 nanometer size, and theoretically when checking it is 1 point less than that, and logically it is 36 only. It is counting the complexity unit. So. Right, sir. In this case, I have tried, because I told that this is reversible bond. So in many, because this sometimes breaks actually for this case when it is imine bond. So we could not crystallize this system. Yes. Right, sir. Yeah. Sir, your that is question is for the metal architectures that I have shown in water catalysis is going. So in water, sir, organic molecule in water, it is aqueous environment, so hydrophilic environment. So catalysis, organic molecule of catalysis we are doing, then organic molecule, it is preferring the hydrophobic environment. So in aqueous solvent, it don't want to stay, so it is going inside the pocket, in hydrophobic. Now after reactions, that one example I have shown, the when size is getting bigger, it has open window, so it is, if it is coming out, it is forming precipitate. In water, it is forming precipitate. And now small molecules, after then again they are coming inside. And also separating how? Because if you adding chloroform in the water, it is forming two layer, and chloroform layer, it is extracting the product. Like this way, this process is going. For these examples, sir, for like last example, nanoparticle, this is heterogeneous catalysis. Our material is heterogeneous, not soluble. So we are just filtering the catalyst, and again we are doing the catalysis. Cage. Yes, definitely by changing the ratio, but actually for ratio is fixed actually. If you're like, if you check the binding and donating side, that ratio will be fixed. If you add excess, then it will form polymer. We are interested in discrete cages, so that's why we are maintaining the ratio just. Now suppose 2 and 3 unit are joining. Now there are 4, 6 also possibly there. 4 unit, 4A, 6B, 8A, 10B. Like that ratio is, if 2 is to 3, then multiple times it can happen. Like 2A unit, 3B unit. Now if you multiply by 2, 4A unit, 6B unit. This is possible. Now which structure it will form, it depends again the angle strain, as I mentioned, angle strain, their stability, those things. Not always. When you are getting single, that system you are focusing. Sometimes various possibilities are there. When one structure is most stable thermodynamically, so that case we are getting 100% conversion. We can, because we cannot separate. This is large molecules. So yes, there are many examples when you are mixing, it is not forming single cage. It is forming mixture. Kinetically, in a thermodynamic, we are focusing on thermodynamic parameters. So most stable cage, if it is giving room temperature, sometimes 60 degrees centigrade, not very high, but we are giving time. Not important here. If kinetic important, then it will give mixture of products. So we're trying to get thermodynamic parameter to be work. Then only we'll get a single unit. So that's why, like this imine cage we are keeping for 3 days, 4 days. Just simply we are rotating and see 4 days. Then we are checking by NMR, by this, whether mixture or single product. When single product, that point we are stopping the reaction, we are isolating the compounds. Right, sir. Yes. Right, sir. Here, one of the example is that this problem. So here I've shown this diamine, trans diamine. It is working with hexaldehyde. It is giving a tetrahedral structure because this geometry, if you see, in vertices, to form the tetrahedral, 3 amine has to sit, and 3 amine, if it sit, it has to be trans, and then it will give tetrahedral. Now, when we have used cis diamine, it does not give a cage. It gave a mixture of products. Suppose 3 units have been stitched, 3 units only reacted. So we did not get, in that case, a single product, mixture of products we got. So in this case, for example, trans only giving the single product. But in enantiomer pure form, trans diamine, RR giving one isomer, SS giving another isomer. Why? Because this orientation, it is directing this orientation. Commercially available. We can also isolate. It is commercially available, not that much, like 5,000 for 25 mg gram. Cis1 we have tried. Cis1 giving mixture. Very broad and mix of many peaks. Right. They're like that one nanoparticle template. As a nanoparticle template, I have used some gas storage, selective gas binding. Like it has a selective pocket. If you change the functions, now we can do several applications. Right, right, sir.
Thank you.